position to store these energy. So these redox flow batteries are really, going to be a big, storage option for bulk storage of electricity. So what is this? It's a combination of battery and the fuel cells. This is a simple fuel cell system. This is battery. Utilizes circulation of electrolyte, from the reservoir to the cell stack. I'll show you what are the stacks and bipolar electrodes kind of thing. Okay, what is the advantage of these redox flow batteries? Actually, whatever the energy storage system we have been talking, lead acid battery, nickel cadmium, lithium ion, the power and the energy density is fixed. So whatever the company gives a storage system, it is mentioned this much energy density, this much power density, that's all. But in the case of redox flow battery, you have a privilege of decoupling energy and power. What does it mean? That means independently you can operate. So for example, look at this cartoon. This is your model. For some application, I may need high energy density. So how to do that? Simply increase the volume of electrolyte. So this is your electrolyte, and increase the electrolyte, you will get high energy. Capacity and energy is nothing but same. And some case I need more power. So you increase the number of cell stacks, that is bipolar carbon plates. So this advantage you cannot have any other rechargeable storage system. So that's where these redox flow batteries finding very, very important role. In addition to that, you will be having other advantages: high efficiency, long cycle life, 20-25 years, and 100% depth of discharge is possible. And of course, this is stored in a tank. It's environmentally friendly. Safety wise, it's compared to lithium, it's far better, because here we are not having any metallic species involved. So how does a flow battery works? As you can see here, the active material in the form of liquid, say anolyte or catholyte, stored in the reservoir or in the tank, depending upon the volume. When you take large, you say tank. If you take small, reservoir. These electrolytes are being pumped into the cell stacks. So this is your cell stack, where actual electrochemical reactions are going to take place. And this is a small prototype device that we have assembled long back when we began this redox flow battery system. So again, here also you see the evolution of this redox flow battery. It's also not a new energy storage system. As you can see here, this flow battery also has its own century history. Started from 1880, the zinc bromine redox flow battery. And recently, this technology has been taken a revisit. How important this, and it involves various stages: vanadium redox flow battery, metal, for example, iron and chromium. And very importantly, people are trying to address recently now, see, lithium organic. So by taking the advantage of lithium chemistry and the advantage of flow battery, they are trying to combine these two to make use of large scale. Because you will have large energy density when you have lithium. If you have flow battery, you have option to decouple energy and power. So these are the recent trends. There are a lot more chemistry involving this flow battery technology. So here we have been working on one or two systems. Zinc bromine redox flow battery, that was the initial stage we have started. The reason behind that, we know we have plenty of bromine in the sea source. And of course, zinc, it's abundant in the earth. So by having that, we initiated this zinc bromine redox flow battery. What are the challenges here? As you see in your lithium, here also dendrite growth is common in the case of zinc. All zinc based system, so this is a common issue. The other issue is the electrocatalyst. So in this case, if you look at zinc bromine, bromine is the cathode, this is anode. So cathode reaction and anode reaction should be same. The kinetics of both the redox reactions should be same. But in this case, bromine redox reaction is very sluggish. It means it's very slow. It's not that fast as your zinc. So you need to enhance the kinetics of this bromine. That is one kind of challenge. And the second part is dendrite growth. So we are trying to address one by one. I'll just show you some of our work where we try to enhance the kinetics of bromine redox couple. What you see here is actually cyclic voltammetry analytical tool in electrochemistry to find out the redox reaction and the kinetics of that. Look at this here. One of my PhD students used, two different carbon nanotube, that is multi-wall and single wall. And the black one, there is no catalyst. The reaction is very sluggish. And you could see the difference when you use multi-wall and single wall carbon nanotube. More importantly, this is nothing but your charge discharge curves. Like in your lithium ion battery, you might have seen charging and discharging. Similar way here, this is charging, this is discharging. Look at this, when you don't have any catalyst, that is black one, there is huge difference in the efficiency, 680 millivolt difference. So the voltaic efficiency of this system is very less. The moment you modify the electrode with the catalyst, and you could see the large difference, the reduction in the over voltage. So that eventually reflects on your energy efficiency. And the new system what we have proposed, because there are issues in the elemental bromine. So we are trying to replace that bromine with the other component called vanadium. Because vanadium flow battery also is a well-known redox flow system where vanadium has issue in the solubility and limited energy density. So in this case, we try to combine like two systems, zinc bromine and vanadium. We came up with a new redox flow system, zinc and vanadium. So this is the progress made on this zinc bromine redox flow battery at CSIR SICRI. So now we are in the capable of having 500 watt cell stacks. So we have been working now various redox chemistry to enhance the energy density of these redox flow batteries. And of course, we are almost at the end. So if these redox flow batteries, it has another advantage. It is easy to transmit from one place to the other place. Okay, so these are the cell stacks. So the cell stack inside, and you can store the container here. These are reservoirs. So when you have a large amount of electricity storage, look at these. Actually, just imagine, suppose you have a tank that is half of your football ground. Then imagine how much amount of electrolyte one can store in that. So depending upon the amount of electrolyte, you can expect the energy density. And by increasing the number of cell stacks, you can expect high power density. So these are the futuristic of this redox flow battery. That's why people are trying to work out to have a viable storage system for solar and wind to store bulk energy, electricity. So with that, I think we are almost in the end. So what is that we have seen so far? We have seen in the first part what is the energy consumption and what could be the energy demand and what are the energy sources that we have been using and whether these energy sources would sustain in future or we need to find out alternative energy storage. So when we talk about the alternative storage system, then we have seen solar, wind, geo and hydro system. And more importantly, the electrochemical energy storage system has taken a major role in this scenario to store energy in terms of bulk or in terms of the large capacity or electric vehicle kind of thing. So this change will happen only finding a new chemistry. The alternative materials only could bring up the energy density to the large extent. As you could see, your lithium sulfur and lithium air, of course, to sodium also. So these are the new chemistry, and we need to address all the challenges, whatever we have seen. So when we come out with a new catalyst to bring down the voltaic efficiency, to improve the efficiency of lithium air and the electrolyte and the active material, all these things to be addressed. So at the end, we always see that the grass always looks greener on the other side, but alternative technologies should be carefully examined for their long-term sustainability. The oil to lithium, so that's what we have been talking, right? Which remains as Woody Allen's word. So what he said, more than any other time in history, mankind faces a crossroad. One path leads to despair and utter hopelessness. The other to total extinction. Let's pray we have the wisdom to choose correctly. So with that, thank you, and I must acknowledge our director and funding agency CSAR, DST for the support. And thank you very much for your patience. Thank you.
Thank you so much, sir, for your time and your lecture.
Yes.
Now it's open to participants. If you have any questions, post it in the chat box. Professor will be free to answer the questions.
Yeah.
One or two quite quick questions,
Yes.
please.
Now 2 3 minutes I have. You can have, or any specific question, then you please write to me. I'll try to address.
Yes, sir. There is already a question, sir.
Yes. Yes.
Tesla is one of the leading company in US has introduced a car which consists of lithium-ion battery that could deliver a high energy density of 85 kilowatt. Why do you think lithium-ion when compared to lithium air or sodium-ion or redox flow battery? Because after 2 years of usage of our mobile phones.
Yes. Yes. So Rupa Ranjini has raised this question. Okay, so the current lithium battery, what the Tesla has used lithium polymer battery, they are making use of lithium iron chemistry. So look at this energy density, 85, kilowatt hour the capacity. And if you want to have more mileage, then the amount of energy is not sufficient. So that's where we have been talking about lithium air and lithium sulfur. So obviously, redox flow battery may not be the ideal choice for the electric vehicles. So only lithium sulfur could take in this place. So that's what I feel in the case of lithium polymer or lithium ion batteries. So the amount of energy is not sufficient to have a long run in the electric vehicle. That's where lithium sulfur or lithium air should be the ideal. So what is the working
Thank you.
temperature? Somebody was asking. Yeah, I keep all these questions and then I'll respond one by one. Any
Okay,
other
sir.
quick questions? Yeah, somebody was asking the redox flow battery working principle. Yes, I can show you. The redox flow battery, it's a simple like your battery. Only thing in other battery system you have active material in the solid form. In the case of redox flow battery, your active material is in the liquid form. That means your solution. So that solution is being pumped into the cell stacks where you have carbon plates, the surface. That's where your electrochemical reaction happening. The temperature dependence, all the chemistry, whatever we are talking, zinc bromine or vanadium, it's all working in the ambient room temperature to 35 to 40 degree. It's possible. Okay. What are any specific? Yes, Kamalashmi. Sorry. Why metal air battery like aluminum air and zinc airs are not that much successful in the electric vehicle? Yes, Tenmoli Ganesh asked. Okay.
Yes, sir.
See, that's why, because we are talking lithium, even lithium also is not successful, associated with a lot of issues. In the case of aluminum and zinc we already know that there is an issue with the dendrite growth and again the kinetics. So all these air batteries are mainly related with the development of the catalyst. If you look at the reaction of oxygen reduction reaction, so that is very sluggish. So you need to have a catalyst which should be used for oxygen oxidation as well as oxygen reduction. So that's all we say ORR, OER. So one catalyst should function both the way. Oxygen should be reduced, oxygen should be oxidized. So these critical challenges only is common for any aluminum air or zinc air or lithium air. Whatever the air battery we talk, these are the bottlenecks we have. Okay.
Thank you, sir. Maybe with
Okay.
this we will wind up this session. Thank you so much, sir, for joining us and deliver your lecture.
Okay.
Thank
Thank
you.
you. Thank you. Thank
Thank you.
you.
Thank you.